So let's start to the first example, and that's the concept of a queue. So what is a queue? Well, it's some concept that is used widely in real life, but also in computer programs. We may want to represent data of various forms that arrives and leaves. And the main structure of a queue is that there is a notion of a front of the queue. So that's where things leave from the front of your queue. And when you join a queue, you join at the back. So it's an ordered sequence of things where the main operations on that sequence of things is joining a queue and leaving a queue. And then we use these kind of structures in computer programs very often. For example, if you are sending files to a shared printer, there is a queue that ensures that they're printed in the order that they arrive. Or there may be lots of different jobs to perform in some computation, and you want to perform them so that the first come, first served, that is the oldest job, is run before any newer jobs. And all of these things require a representation of the data that implements this concept of a queue. Now, you know from real life that there are notions of queues that we deal with every day, and the implementations of those can be very different. But the end result is the same. The people that arrive first get served first, even if it can be an inefficient implementation and involves you standing in a line, or a more efficient one involving taking a number ticket and being served in the order that the tickets are taken. So just like in real life there are different ways of implementing the same basic idea, we also see this in software and in computer programs. So what we're going to look at then is the first example today is an implementation of a queue. And we're going to look at two versions, one which is in some sense rather inefficient, and another one which is more efficient but won't be involved taking numbers. In fact, it'll be quite a different representation. So let's switch to a editor buffer here and start looking at what we expect from a queue. So the first version of a queue we're going to look at, and you can tell that one of the main features of it, we're calling it a slow queue, but the main thing is that a queue, an abstract data type like a queue, has an interface, and that interface consists of a bunch of functions for creating and manipulating queues. So we're going to introduce shortly, we haven't done it yet, a new data type to represent a queue. This will be the implementation, this will be the data structure that we're going to use. But independently of which choice we make, the thing that we want to implement are a bunch of basic operations on queues. For example, a test, a function for creating an empty queue. A function for adding an element to a queue of elements to get a new queue. That'll be the slightly bigger queue. So that'll be the result of conceptually adding the element to the back of this queue. And the reverse operation that we get called remove, which is the queue we get by removing the first element. So this is, we start with a queue and we remove the first element, we get back a queue. Now this actually will be an operation that can fail. It will fail if the queue is empty. So in that context, then it's rather useful that we also have a predicate is empty to actually test whether a queue is empty. And similarly to the remove, which removes the first element from the queue, we also have a function that gives us the first element. So if we were to put this element back on the queue that we got by removing, we should get back to where we started. And that's a little hint that we'll be actually interested in defining properties to specify properties of any implementation of such an interface we expect to be true, regardless of how we implement it. So what is a good way of implementing a queue data type, a queue of things, and it doesn't matter what's in the queue? Well, we have a data structure that's pretty handy for that kind of thing, and that is a list. So we could represent a queue of things using a list. And representing a queue using a list will be the most straightforward, but not necessarily the most efficient. So let me just derive a couple of functions here in case we need them at some point. I don't think I'll need a queue, but certainly show will be very useful. Okay, so having chosen to represent the internal representation of a queue using a list, we can now get on with the job of defining the basic operations that we want for queues. So the empty queue is defined by the constructor for building a queue, and the contents of the queue, which will be represented by the empty list. Adding an element to a queue, we have an element A and some queue. Let's construct a queue and the remaining elements. So what we need to do is put the new element at the end of the queue. And what is the end of the queue? Well, we're representing a queue by a list. So we have to decide whether the front of the list is the front of the queue or the front of the list is representing the back of the queue. So I'm going to represent the front of the queue using the front of the list. So the new element that joins the queue has to not go at the front, but at the back. So to put an element at the back, we use an operation that we saw when we were defining the reverse function naively, the simple version of the reverse function. To put an element at the back of the list, we need to use the append operation in that way. We make a singleton list, a list of just one element, and we join it with that. And in this way, we put the new element all the way at the far end of the queue, at the end of the list that represents that queue. Okay, that was the add function. What about the remove function? Well, we're going to do pattern matching in a similar way, but remove will only work if the queue is non-empty. So we're going to pattern match on the non-empty list in that way. And we're going to then generate the queue that we get by removing that first element, namely the rest. And we can make that a bit clearer if we use the don't care pattern, but that's not so crucial, so I won't bother about that now. What about the front of the queue? Well, the front of the queue, that's a very similar operation. We take the queue of the same shape and return the first element. So this is the queue that we get after removing the first element, and this is the first element. Now, when is a queue empty? When is a queue like that empty? Well, again, we could use pattern matching for this, but I'm going to use a little bit of pattern matching, but I'm going to fall back on the standard list operation null, which tests whether a list is null. So a queue is empty if the list inside it is null. It is the empty list. Let me just tidy those guys up, and we have our first implementation of the abstract data type of queue. And this is going to serve as our reference implementation for when we implement a smarter version and not such a slow queue. So this is called the queue. This is wrapped up in a module called the queue slow version of the queue. And we're going to use this to define the fast version, or rather to test the fast version.